So thank you everybody who is here for this. This topic is about valuing green stormwater infrastructure. And we have two presenters in this section, Dr. Dan Mills, who's going to be talking about seeing more than all there is, how groups learn to appreciate the value of green infrastructure. And a little bit about Dr. Mills. He's an assistant professor of environmental planning in the Center for Earth and Environmental Science at Plattsburgh State University of New York. His research focuses on the judgments that inform collaborative environmental planning, and he draws practical examples from extended case studies to show how planners how to improve and enhance plan-making judgments by overcoming obstacles like cognitive biases, spatial scale mismatches, and political disputes. His work is substantially focused on water resources like water supply planning, water quality planning, and flooding, and especially water-based planning and management. So that's a little bit about Dan, and he's going to be speaking first. And then we also have Kerri Watson over here, who's a PhD candidate. She's going to be talking about the economic valuation of flood mitigation services. And Kerri is currently pursuing a PhD at UVM in the Gund Institute for Ecological Economics. Originally from Baton Rouge, Louisiana, Kerri has worked for the past year on a Payments for Ecosystem Services project in rural Haiti. She is broadly interested in how development can be balanced with the conservation of ecosystem services and biodiversity. As a graduate student at UVM, her research will focus on quantifying and mapping ecosystem services across the state of Vermont. So we'll have Dan present first, and then Kerri will follow up, and then afterwards is the keynote speaking session with John Todd. That's going to be over in the Silver Maple Ballroom, so we can all walk over there together after in case people don't know where that is. And with that, I'll turn it over to Dan.
So I see like 5 of the 7 students from Plattsburgh that probably made it here. I'm going to, since you're all my students, I'm going to mandate that you stay through Kerri's talk. Okay. All right. So thank you for the introduction. I am Dan Mills. I'm going to talk about so seeing more than all there is kind of my riff on Daniel Kahneman's "What you see is all there is," which sort of reflects this notion that we sort of make decisions from the tip of our own nose, from our own perspective. And a lot of the work that I'm going to be talking about is based on research that I've been working on with a bunch of collaborators in Chicago. So I need to get my whole thing warmed up here. I always like to give the punchline for my talks at the beginning, so that way you all can go back to Facebook and Twitter and Instagram. But the deal is that we'll be talking about ecosystem services and green infrastructure, valuing those things. And I'm going to be talking about maybe a little more than just dollars and cents values. Okay. The thing that I want to talk about is how we go about supporting making common sense judgments or non-common nonsense judgments, better judgments for planning. And then focusing on judgments that are value-based and not value-biased is a key distinction there. It's important to incorporate values, economic values, personal values, whatever, in making decisions, but we have to be careful not to let those values bias us in a particular perspective or towards particular ends, because we might miss opportunities for making better decisions or more effective decisions. And we might believe that our biases, our values count other people's values, and that's not necessarily always the case. So, a little bit of how I got started and how I learned the value of natural capital. Sorry for the terrible image. This was literally taken on the first digital camera in 2001. And you can see right here in this tiny little pot, I'm not in the picture, by the way, because I took this. And I'm not kidding, it was like the world's first digital camera. It's this tiny little tree, and so this is at Roanoke College where I did my undergrad, and the name of that tree is the baby bittle tree, and there was this whole big long backstory. This larger bittle tree was a tulip popular, and it was like 150 years old. It had been planted by the founder, and we were all excited that we stole some seeds from the grounds and actually planted it in one group. So we decided to plant it on campus, and we made this whole big thing. It was like another one of those ribbon cutting ceremonies. And the president walked out and came, this is his office is in this nice fancy building here. He comes walking out and he looks in the pot and he goes, "That's it?" Right? Like, oh, gee, that's awesome. But the great thing about it is that this was the same tree 2 years later. Okay? So almost immediately we're starting to see, it's got a shadow. I can throw a little blanket on it. And then by 2006, I can actually stand underneath it. And here is that same tree as of 2012. This is a Google Street View. I haven't been back, so I don't know how much bigger it has gotten in the last 4 years. But it's an actual tree now. So I learned very quickly that not only can we identify economic benefits from this, but the thing is, this tree kind of started to become a focal point of campus in the same way that the other actual large middle tree, which gas was cut down because it was a street fall hazard because of storms, it actually dropped a very large limb. They do graduation like out here, and it dropped a very large limb to about 200 chairs. And it had happened during the graduation, like a bunch of people were, not survived. So the other way that we talk about, valuing ecosystem services and green infrastructure, we throw out these two terms. I just want to throw, this is a Google Ngram. You guys ever played around with this? It's really cool. You can see when things became popular. So, turns out that I was sort of doing the undergrad thing right when green infrastructure became a thing, right? Right in 2000, it sort of started in the early 90s, and right by 2000, it's like, boom, green infrastructure was suddenly everywhere. Ecosystem services is a concept and an idea that's gone back to the sort of late 70s. And sort of values or incorporating values kind of tries to link the two together. Green infrastructure provides ecosystem services and you can assign a dollar value to that. So you know this paper. You have to know this paper, right? This paper has been cited 15,000 times. So this is Costanza's paper on valuing the world's ecosystems. And I'll just see if I can pull the thing out in that section. Okay, so these authors, this is Nature, it's a very prestigious journal, and they calculated that the entire biosphere, the value of the estimated value in the range of 16 to 54 trillion, a large error bar, US dollars per year. The average is somewhere on the order of 33 billion trillion dollars per year. So you can assign these dollar values to the ecosystem services that the natural systems provide. Okay. But if you were just in the room a few minutes ago, I asked the question, how do you translate that sort of theoretical economic value into cold hard cash? Okay? To illustrate this concept, does anyone have a 20 on them? Sweet. This is going to be perfect. Okay. You don't know this yet, but you're actually going to lose a bet for that $20 bet. I'll give it back. Okay? All right. So the stakes are this $20 bill. I did not give it, I know he's my student, but I really didn't give this to him before. Okay. So, there is something wrong with this. Okay? And I'm going to use an ecosystem service, something provided by nature, to take this $20 bill off my front here. Okay? There's something wrong with the image. Does anyone know what it is? Okay. This is the same building, no? Okay. This is the White House. Right? Okay. Looks the same. Let me back up. We can all agree. Okay, this engraving for this $20 bill is maybe in like the 30s or something like that. Okay? You ready? Wait for it. Too far away. See it? And back up. Watch the west wind. Okay. It's a good show, but that's not what I'm talking about. What are those people? Nope.
The tree is.
See it? Right, so I just turned that tree with $20 bill. The truth be told, I don't know back. This is college students, he needs it more than I do. The truth, so these two images were actually taken about a month and a half apart. And yeah, there's these two famous elms. They were supposedly planted by one of the Roosevelts, I think it was Teddy. And the other one on the west side of the White House is gone. And there was a very large storm event on June 29th of 2006 in the DC metropolitan area. I remember this because the play I was interning in DC for Casey Trees, doing urban forestry stuff, learning about the economic value of trees. And there was this big storm, and the tree just fell down. So you can see, you notice something was different, right? But you don't necessarily appreciate it fully because you're sort of looking for other things that might be different. You don't really notice the nature that's around you, right? So we have our whole currency, $20 bills, have this image, but we don't really see that it's there, right? So we have to find a way to not only turn economic value into cash value, but also to help people recognizing the benefits in more sort of explicit ways, right? So what I want to talk about is this notion that environmental problems, and my students are all going to groan because I talk about this all the time, are really quote-unquote wicked problems, okay? And I don't like to just throw out wicked problems without actually talking about what wicked problems are. So I like to talk about the 10 attributes. Now, not all problems that are wicked meet all the 10 attributes, right? So I'm just gonna, so there's no definitive formulation of what the problem is, okay? This is from Rittel and Weber, it's a great paper, go read it. There's no stopping rules, you don't know when you're done. Solutions are good or bad, they're not true or false, so one solution is not necessarily more better than the other, they're just some are good, some are bad. There's no immediate test for effectiveness. There's these long lag periods between when you put a solution in place and when you actually see an effect. There's this irreversibility problem. You build a large piece of infrastructure, you kind of can't do it, the whole sunk cost thing. There's no fully enumerated set of solutions. We could go on and on and on and on, but we're still going to be chasing our tail, finding more and more solutions. We're finding different ways and solutions to work together. Every site condition is unique. Context matters. Problems are symptoms of other problems. I just had a great talk, I can't remember the gentleman's name, talking about how if you manage for pollution, you're also, and they were talking about pollution, the link between pollution and flooding, and link between water quality and economic growth. So there's all these things that when you step from one symptom of the problem, you step immediately into another problem. Framing matters. How people explain the problem is also really important. And people will frame the problem differently. And then there's, when you get to, I just talked to Kevin Barrington, the engineer from the city of Plattsburgh, before coming in here, city officials or public officials, they have no right to be wrong because the consequences are pretty severe. So if you make a mistake, right, in Flint, the consequences are pretty disastrous, right? I don't want to talk about all of these today because that's just too much. I want to talk about sort of this solution ending, because we all think green infrastructure is the solution to our stormwater issues. And I'll focus on sort of this idea that solutions aren't good or bad, they're not true or false, they're sort of good or bad. Some work better than others, some work in different ways. I also want to talk about how that there's no complete set of those solutions, and there's no single one solution that's going to work better than others. There's no optimal solution. And then the last thing is we're always chasing this unique condition. Wherever we go and try to do stuff, things are going to be slightly different, right? And the conditions even in a particular location are going to change, then climate change, okay? The other part of this, right, is we could focus on that. But the problem that you really have is to get at those things, you have to overcome this no immediate test problem, and you have to overcome this irreversibility problem, right? You can't really do the work, right, to understand if any of those solutions are going to function as well as you think they are. Because if you build something, you can't unbuild it. You can, but it's more expensive, right? And the other thing is that you have to wait in some cases. The example that I like to use is the flow time for groundwater flow on Cape Cod. And I did some work out there where folks were working on water quality issues on the Cape. And when a drop of rainwater landed in the center of the Cape, water would go into the soil because they've got really sandy soils in the beach. And it would take anywhere from 100 to 150 years for that drop of water to make its way through the sand and underground aquifer out to the estuaries. So that water, that bulk of water, becomes polluted. Okay, I always used to tell folks, the water that's emerging in the estuaries on Cape Cod now is polluted with effluent from when Kennedy was still alive. So you can literally go swim in the estuaries in Cape Cod and be swimming in a former, or not alive president's former effluent. It's treated now, but that's how long it takes for some of this water to move through, right? So if you put a treatment thing in place, and you put a permeable reactor barrier or constructed wetland, right, it's going to take time for that treatment, that solution, to translate into some measurable outcomes. And we're all about monitoring and establishing measurable outcomes, but when you're working in the future and you're trying to make the case that we need to invest in these things, it's really, really imperative to shrink the time, right, into a few minutes, so that people can assess and evaluate what the solution is going to do and when it's going to actually work, right? So there's this temporal cognitive barrier, right, that stands in the way of people actually translating this stuff into effective change, okay? Right. So how do we do that? Okay. This is the old school model of science, right? Everybody recognizes this from my biology? No, of course not. It's a friend of mine, a colleague of mine in Chicago, when I was down there, sort of wrote this paper in 2008. You should actually, if you ask her, she wrote it in the mid-90s, and then the journal reviewers would never let her publish it. But basically, there's this gap here between scientists building models and analyzing systems, and this policy world where policymakers and citizens are using those predictions, those assessments, those evaluations to make decisions. Okay? And there's a sort of assumption of objectivity that on the part of the scientists, right? We're making these objective analyses and coming up with objective results, and our predictions are infallible in a lot of cases. And it's not always true, you know. And so what we're trying to do, what we've been trying to do, is finding ways to integrate the sort of modeling work, the sort of assessment and evaluation work that scientists typically do as a matter of their jobs, and integrate it more in participatory settings, right? So if you watch the model setting here, it shifts down into, see, I gotta stop standing so far away, into the sort of this sort of integrated analysis and assessment frame, okay? I just want to spend the rest of the time talking about an example of pertinent to green infrastructure. So this is a model, an agent-based model that some of my colleagues built called the Landscape Green Infrastructure Design Model, or the LGRID model. So think of an urban neighborhood. I'm just going to snap this. And the gray areas are the gray infrastructure, it's roads. The brown areas are permeable cover, so lawns maybe not as permeable, but semi-permeable. And then there's the green infrastructure. I think they did bioswales here. This is a very stylistic tool, right? The whole point is it's not supposed to be precisely accurate. It's more stylistic to help people engage in trade-offs. You have roads, you have outlets, you have sewer intakes, and water is flowing. The sort of this topography, it's higher over here and lower on this end of the map. Okay? The model itself processes a number of natural processes. That was very important. It starts with a rain event. It lands on one of those three land covers. So the water and the model then sort of model what the infiltration is going to be like across those three land cover types. Water will collect and go to sewers and translate into flow in the sewers. This is far more complicated when you actually look at the code. Trust me, that's why I try to avoid it. You get some evaporation, so we actually will model how much water leaves the surface through evaporation processes. We'll look at evapotranspiration. And then lastly, there'll be surface flow. Not lastly, and then there's outflow. Okay? So the whole point is, with the surface flow and outflow, it's whatever's left on the landscape will turn into a sort of urban flood, right? Here's the upside of this. So we make this model, and then we want to, like I was saying before, we want to take this model and plunk it in a room with stakeholders, with people who are making decisions about where and when and how to implement green infrastructure, okay? So we're looking for building solutions and identifying compromises, how people engage in value trade-offs between their different perceptions of how green infrastructure is supposed to work. Helping folks identify and become aware of their own preferences. In a lot of cases, they might not even know what they prefer, right? Addressing those sort of diverse needs, diverse values. And then, again, not focusing on a single magic optimal solution, but focusing on suites of solutions and trade-offs between different techniques and how they function together, all right? So, this is an example, and what we've done is translated that first initial LGRID model into something a little more tactile. And you can see, these are some of our stakeholders, some of our research team, and they actually have a map, and you can't see it because it's like hung from the ceiling, but they actually have these tokens, and the tokens represent different types of green infrastructure. They can choose where to place the tokens on the map. The overhead camera will read what's placed on the map, and we'll actually project it back here. You can see the model, the LGRID model, running on a computer screen. So the camera will actually translate the model map that they've made, that they've negotiated, that they've come to an agreement on into a model world, okay? The other thing is, and you can't see it because it's sitting flat, we have these iPads. We have like hundreds of them. I've never seen so many iPads in one location. And what on the iPads are these individual user interfaces. And what they'll do is they'll allow people to sort their preferences. So do I care more about impact on my neighbors, or do I care more about lowering investment costs? So it's a way to force them to make choices and really consider what they prefer. Okay. And then when we run the model for them on their iPad, they will actually see a ranked score. Where is it? Of their trials compared to their profile. Right. You can actually see the trials will actually produce a flood map. So these are the areas that were most damaged. The other thing is that when it runs, will actually, the group will see sort of a bulk cost estimate of what it costs to install versus what the damage costs were. Okay? So the idea is we're giving them, we're allowing them to engage with their own internal values and ranking their preferences, but then giving them sort of an outcome, an immediate outcome. And these models will run, if they're set up right and optimized right, the models will run in a couple minutes or less. Okay, so we'll see these immediate effects. And they can do multiple trials, right? So the upshot is they can make those trade-offs. Okay, so just a few quotes. So that's much better for you, but not for me. So if I look on your preference ranking, then you can see you did really, really well, but I didn't do so well with my score. I guess it matters what your priorities are. Folks will start to recognize that what we do is a function of what our priorities are as much as it is a function of what works better. Damage was reduced by 87%, but we're over budget by 1.2 million. Right? So the key is how do we lower the overall budget and reduce the damage? It allows people, this is getting back to the wicked problems stuff, it allows people to do systematic exploration. So some of our stakeholders talk about, like, let's just throw everything on the map and see what happens. Damn the consequences, damn the costs, just put it all out there and see what happens. Okay? The other thing is they're reflecting on this is that we can do this multiple times. You don't need to stand around and wait for monitoring. We can try out different suites of implementation and see what happens. On the more cognitive side, right, even sort of like the design aspect of this, it allows people to engage in, like, how do they understand flow? You see them making sweeping gestures over the map, right? You'll see them making sort of building imaginative stories about how things could be, and they're like, well, what if we tried it out? I played around with this, what they call it, and we talked about coming up with the Cadillac versus the Chevy plan versus the VW Bug plan. And then the last thing, and this is sort of more where my research sort of fits in, is recognizing the spatial relationships and spatial constraints. Maybe we need to move houses out of it. Maybe we shouldn't be building houses and floodplains and then insuring them for making bad choices. How do we consider not just green infrastructure by itself, but how does it relate to our existing gray infrastructure systems? And then how do we coordinate, mention regional planning? Like how do we motivate regional coordination and cooperation? How do we motivate cooperation between two neighbors? So all of this stuff allows people, all these models allow people to engage with all these various things in a lot of different ways. We see a lot of rich interaction as people play with this thing, right? So to wrap up, just wanted to point out that when we're talking about valuing green infrastructure, we're talking more than just economic, more than just dollars and cents. That we're trying to support common sense judgments, that we're talking about value-based, not value-biased judgments. And I'll add a couple. Technologies, we're sort of playing around with this idea that technology can function as a cognitive prosthesis. That our brains can only think so far at a time, but we can use the tools to sort of overcome our natural barriers. And then we're seeing that these tools are really critical for engaging into the messy complexity of democracy and then sort of messy complexity of the real world. How do people learn to understand these systems better, and how do they actually learn to cooperate? Whole lot of people to thank. I won't read all of them. The three at the top were the sort of three key folks that worked on this model that I showed you. Moira Zellner, who's the lead PI, Joey Shelley, and Dean Massey. Joey's doing the HCI, the human computer interaction stuff for maps and models and model. And Dean is the chief model builder on our team. Really sharp people. National Science Foundation funded us. UIC, University of Vermont, Chicago gave us some funding. And then I have to mention my supporters now, the Center for Urban Environmental Science at Plattsburgh State. And that's me. Thank you very much for listening to me ramble for 25 minutes. Did I get the number?
Yeah.
All right.
So we have like 5 minutes for questions. If anybody has questions, and I'm just going to pass around the mic if you have them. We're recording all these presentations, so we're just trying to capture the questions. Sorry. It's a pretty thorough presentation.
Done.
Killed it.
Just drop me if I drop mine.
The David Center mic is a little mad. So yeah, now we'll transition over to Kerri Watson.
Thank you.
Pulled up.
Behind here?
Yes, actually, if you go, it should be the other open PowerPoint tab. Yeah,
Oh,
that
awesome.
looks like you. And then if you want to hit present, I'm going to see that should work. And nothing's being cut off. Great. Okay.
Great.
Sweet.
Awesome.
All right, all you.
All right. Hi, everybody. I'm Kerri Watson. I'm a graduate student at the Gun Institute here and at the Rubenstein School. And I was asked to say a little bit about how I came to be doing natural infrastructure research, in case anyone in the room might be interested in doing that, which I imagine is true. And just to build off the graph that you were showing about ecosystem services and natural infrastructure as terms, I actually was looking for grad programs in ecosystem services and now have found myself in this world of natural green infrastructure because I'm doing a lot of stuff on phosphorus retention and flood mitigation. So if you're looking for internships or things to do about those issues, that's another way to look for them. So this framing has already been set up pretty well by the previous presenters, but essentially I'm thinking about green infrastructure and the way that it can potentially mitigate negative impacts of climate change on people. So green infrastructure I'm thinking of as components of ecosystems that can reduce these climate change impacts. And specifically, the work I'll be presenting today is about the role that wetlands and floodplains can play in reducing peak flows and looking at that impact on human well-being in terms of damages that occur downstream and how those are reduced. So avoided damages, we've been talking about economic valuation, is one way of coming up with an economic value for this effect of natural infrastructure. And that's the one that this particular study uses. So flood impacts are really important here in Vermont, but this is just to make the point that with with climate change, we're actually seeing increasing precipitation across a majority of the United States. And so green infrastructure is really valuable now, and it's only going to become more important in the future in terms of mitigating floods. So this is just a map of precipitation, and you can see that all of Vermont, I think all of New England, and a majority of the United States is in this blue-green realm, which means that precipitation is increasing. And actually, if we look at this other map, also from the National Climate Assessment, you can see that those precipitation increases are actually being registered at gauges on our rivers that are put in by the U.S. Geologic Survey in terms of the peak flood events that are happening there. And so when I look at this map and that precipitation map, I take out two key points. One is that this overall increase in precipitation that's happening with climate change is really going to be important for flood mitigation. It's not happening in dissipated events throughout the year. It's actually happening in an increased frequency of big storm events that's getting registered as floods. The second thing I take from this is that this is already happening. So we can think about the role that green infrastructure is already playing in mitigating climate change impacts. So we know that floodplains and wetlands can have this impact of mitigating floods, and we know that floods are a huge issue here and globally. In fact, flooding is the single most common natural disaster, and it's the one that consistently causes the most human deaths globally. So if we know those two things, why are we continuing to see wetland loss and the degradation of floodplains? There's a couple of reasons that might be happening. One of them might be that this value of floodplains and wetlands in mitigating floods just isn't actually internalized when people are making decisions about how to manage landscapes. So one reason people value this natural infrastructure or these ecosystem services is to try to facilitate the use of that information when people are actually making decisions. Another reason it might be happening is that while they might be highly valuable, the people who would have to incur the costs to protect wetlands and floodplains are very different in many cases than the people who are actually going to benefit from that, even if the net benefit is positive. But overall, I think if we can quantify that effect, we can really facilitate the use of this piece of information that wetlands and floodplains can mitigate floods. So what we tried to do is take a case study here in Vermont, which was Tropical Storm Irene and flooding that happened along the Otter Creek, and see if we can find a way of simply but justifiably putting some quantitative estimate of the impact that these wetlands and floodplains in blue had on flood damages in Middlebury. So if you're here in the former session, just full disclosure, they were talking about this study, that was me. So there's already been, my scoop is stolen, but I'll add some detail. So if you look at these two graphs, what happened during Tropical Storm Irene is that we had a big flood pulse. And there's a USGS gauge right here in Rutland, and there's another one in Middlebury. And this is a great example for me. For there's one pointer, if you want a pointer. I can use this so I don't block my own picture. So this is a great case study, for one thing, because it's already been recognized that these wetlands and floodplains are important. And people were trying to find a quantitative way of explaining that, and so that there was that need. But also this is like the perfect natural experiment, right? We're measuring floods here, we're measuring floods here, and this wetland floodplain complex is perfectly constrained by those two gauges where we have hydrologic measurements. So we jumped on this opportunity. And this is what those hydrologic measurements look like. These are hydrographs. So along the x-axis you have time, and along the y-axis you have discharge, which is cubic feet per second of water passing by that gauge. And what you see is that in Rutland, this peak is huge. All of the water came through Rutland at one time. The water continued to flow downstream through those wetlands and floodplains, and by the time they got to Middlebury, the peak was much lower, which means that the flood level was lower, even though that curve on top represents twice the total volume of water, because you have more water entering the stream between those two gauges. So we wanted to answer two specific questions. The first was the value of those wetlands and floodplains for this specific event, Tropical Storm Irene, which is useful as an example, but we also wanted to try to get an estimate of what's the mean value on an average year of these wetlands and floodplains, because that's a more useful number if you're planning for the future. Because understanding that the impact on Irene was huge is great, but we need to know also how often are storms like Irene going to happen? What is this impact like for bigger and smaller floods? So you can come up with kind of an estimate of over time what's going to be the payback of having these wetlands and floodplains there. To do that, we laid out this 5-step process. We needed to know what that hydrograph would look like if the wetlands and floodplains hadn't have been there. Then using that hydrograph, that alternative hydrograph, we could look at the change in the total extent of flooding in Middlebury and identify flooded structures that would have occurred, that would have been flooded in the case without wetlands and floodplains, but weren't in reality because the wetlands and floodplains protected them. And then we could look at the total value of damages that were avoided to those buildings that were flooded in one case and not the other, or were flooded worse in one case than the other. Then we performed that same analysis for many, many floods through time to come up with a mean annual estimate. So I'll just run through this quickly. Here you see again, Rutland is the upstream gauge before the water went through wetlands and floodplains, and you see the high peak, and Middlebury is the low peak. And actually, we created 2 alternative scenarios because it's kind of hard to estimate that impact. So the dark blue line is the maximum flood that we could conceivably think would happen if those wetlands and floodplains hadn't been there. And then the light blue line, which is not showing up well here, but it's like right about where Rutland's does, is a lower case scenario. And we think this kind of bridges the scope of what that impact might be. And so we use those flood peaks to translate them into the actual elevation of the floodwater in Middlebury. So here you have in the gray line, this is just like a cross section looking across Middlebury, and you see the stream channel right there. And this gray line is the elevation that actually happened after Irene. And then you see the light and dark blue lines. These are our range of the elevations of flooding that we think would have happened without the wetlands and floodplains. So this is just a cross-section in one particular point on that river, but we actually used high-definition satellite data, LiDAR data, and flooded that landscape in 3D. And that enabled us to get the entire extent of that area that was underwater. And then we could identify structures that were flooded in each case. So in reality, our model predicts we find 9 structures that were flooded somewhat following Irene and Middlebury, as opposed to 21 to 54 structures, we estimate, if the wetlands and floodplains hadn't have had this effect. And here are maps of actually those flooded structures, the flood extents, and where we think they might be. The next step is that we looked at each of those structures and the depth of flooding that happened there and used functions used by FEMA to estimate, based on flooding depth, the economic damages that would probably have been lost in each of those homes. And so you add up the damages in each of these cases. You come up with about $100,000 in the case with wetlands and floodplains, and between $600,000 and $1.9 million without wetlands and floodplains for this one storm event. So what's really interesting is that difference. So the difference between these 2 cases without wetlands and floodplains and what actually occurred. And we find that that difference is worth about $500,000 to $1.8 million, which is a big range and kind of small numbers, actually. But the percent reduction in those damages is between 84 and 95%. So that's really huge in terms of that impact. So what we did next is we needed to find a way of taking that one-time event and using it to predict what would happen in an average year. So what you have here is a curve with discharge, which is what we talked about on the y-axis for those hydrographs, the amount of water passing the gauge, and then the annual probability on your y-axis. So it's really likely that really small flows are going to happen in any given year, but it's really unlikely to have really big floods in a given year. Then we looked back at historical records of flooding and found storms all across this range. And then we used those recorded storms at both gauges, performed an identical analysis to what we did for Hurricane Irene for each of these storms. So I'm just showing 4 here, but we did 10 different floods. So then we had the annual probability, and we could associate that with the damage reduction in each case. And that's what you're seeing here. The damage reductions are on the y-axis, and the annual probability is on the x-axis. The gray is with wetlands and floodplains in place, and again, the dark blue is a high estimate of what would have happened without wetlands and floodplains, and the light blue is a low estimate. So because probability is ranging from 0 to 1, you can do some nice math, and the annual expected value of those wetlands and floodplains is the integral of the area under this curve. So what we wanted to know is what's the difference in that area. So what area lies between the blue curves and the gray curves? And that's the expected value of those wetlands and floodplains in reducing damages. So for our low case, that value is a little over $100,000 per year. And in the high case, it's almost $500,000 per year. So there's a lot of wetland and floodplain upstream of this that's causing this effect, but we would expect this to occur on an average year. Some years there's going to be no value essentially because there wouldn't have been a flood to mitigate, but some years you could expect it to be much, much higher than this, as was the case for Hurricane Irene. So a couple of key conclusions. I went really fast. A couple of key conclusions that we have coming out of this study, thinking about valuation of this project. When I look at the results that we got for this case study and compare them to things that have been found elsewhere, I find that the biophysical effect of what was that reduction in the flood peak is really pretty similar to other studies. And in fact, our high estimate, where those floodplains really have a huge impact in reducing floods, is much more analogous to biophysical impacts I find elsewhere. But when we look at that economic value, it's so low. It's much, much lower per acre, essentially, of wetland or per acre of floodplain than things I've found elsewhere. And I think this brings up a really important point about valuing wetlands and floodplains. We took an avoided damages approach. And so that means that how valuable those wetlands were was directly a function of how much stuff was downstream, potentially to get flooded. And Middlebury is a small town. So the more things you have in your floodplain, the higher that value is going to be across the board. And so our big conclusion from this study is that it's hard, really hard to estimate with any kind of precision that biophysical effect of wetlands. But when we try to bridge a range of plausible effects, we find that throughout that entire range, that feature is highly economically important because there are houses in the floodplain. So that means that where there are things in the floodplain, houses, bridges, to be flooded upstream, ecosystems are likely to be valuable in mitigating floods. One additional thing we found that has been found throughout the natural infrastructure literature is that flood mitigation and its effects in decreasing floods, these natural features are more effective at mitigating smaller floods than mitigating larger floods. Just the ability of that ecosystem to hold back water and soak up water at some point gets overwhelmed. So that's a useful piece of information. In planning to avoid floods, I think it's going to be a mixed approach of you're going to need to keep houses out of a flood zone as much as possible, which is pretty self-explanatory, but clear that that is the most effective way to reduce your damages. You're going to be able to use green infrastructure to mitigate the size of these impacts for smaller events, but there are going to be big flood events where green infrastructure is not going to be able to help as much. So that's all I have for the main part of my presentation. I have more details on different steps of the analysis if people have questions ready to go. But first, I have a lot of people to thank. Mike Klein, Ned Swanberg, Arnie Bombleys, this entire list of people provided me with a whole lot of advice on how to go through this process. And I'm funded by the USDA McIntyre Stennis Program and the Cree Lentilak Foundation. And of course, all of my co-authors on this project. Thank you.
So does anybody have any questions for Kerri? We have some time now before the keynote speaker, John Todd, that's going to be at 4 o'clock in the Silver Maple Ballroom, sort of like directly this way. But if anybody has a question, I'd be happy to come around.
So you've got a bit of a conundrum then. If you hold the houses or don't allow development in the floodplain, you eliminate
the economic benefit of having the wetlands there?
If you take a damage avoided cost approach,
Yeah.
you thought about any ways out of that, kind of taking a different approach to what the value the wetlands will provide, or?
Well, I think that's accurate. I don't think I actually feel a need to find a way out of that. So I think a lot of times when you're talking about valuating these things, the value of it for a particular purpose can get mixed up with its value as an entity. And in this case, I'm valuing the function of that floodplain and those wetlands in mitigating floods. And it's correct that if there were no houses downstream in Middlebury to be flooded, the value of those wetlands and floodplains in preventing floods in Middlebury would be zero. But that doesn't mean that the floodplains and wetlands aren't worth anything. They're worth a lot intrinsically, but also you can think of all kinds of other green infrastructure functions, like taking phosphorus out of the river, or just other values for people, like the way these wetlands are used for recreational purposes, or used by wildlife. I'm a bird watcher, so that's important to me. So to say that the value would be reduced to nothing if you moved houses out of the floodplains means specifically that the value for mitigating floods would be reduced for nothing. And I think that's true. But that should never be conflated with the fact that the value of the wetland would be reduced to nothing. In the same way, these numbers are like crazy if you think that's all that area is worth. But I think they make a lot of sense in terms of mitigating floods to a small community.
So your analysis point was town of Middlebury, right? And for the cases where there were no wetlands, I'm curious what land cover was replaced for wetlands in the modeling?
Yeah, so,
What considerations are the resulting hydrograph?
yep, here, I'll pull up the two hydrographs. So these are really simplifying assumptions. In this high case, we assumed, so first of all, we couldn't distinguish the impact of wetlands from the impact of this really wide floodplain. And that floodplain is unique in Vermont because it is very large and very wide and therefore has a big storage capacity, but also it's relatively intact in terms of its functionality for flooding. So I think in the previous session, people were talking about bank armoring or river straightening, and all of those things would mean that a floodplain, even if it's big like this, wouldn't function in storing water. So those are two pretty different components: wetland as opposed to a different land cover, and then intactness of the floodplain, which is largely topographic. We just clump those two things together for simplicity and assume that collectively those effects are going to change the timing that floodwater, the timing of floodwater getting downstream, but it's not going to affect the total volume of floodwater at all, which is not necessarily true, not true at all, but is conservative. And so this high blue line, we essentially take the volume of floodwater for the Middlebury curve and redistribute it into a shape that's similar to wetlands. So saying that the shape of that curve would have just been conserved moving downstream. And that's really analogous to like piping all of that water in a frictionless tube from one location to the other. So this high case should really be interpreted as like, there's no way the value is higher than that. In the low case, we tried to like take the opposite bar. We're like, we assumed that only the volume of water that was already in the channel when it passed the Rutland gauge was impacted by wetlands and floodplains at all. Whereas we know that about half of the water that flooded Middlebury entered between those two gauges. So that reduced our peak a lot. And then we also looked at statistical averages of effects of other things like channel friction, and just as a flood peak moves downstream, it's naturally going to attenuate, regardless of whether wetlands and floodplains are in place. So we look at that mean effect statewide and cut the peak down as well, according to that. So that we think is like a low bar, but not necessarily a minimum on that effect. So actually, when we look to the literature, we find that the percent reductions most closely found elsewhere most closely resemble those we find for our high case, which actually surprises me. But
Any more questions? I'll take one or two more. All right.
all right.
Cool. Well, thank you all so much for coming.